Welcome. In this demonstration, we're going to work with hypothesis tests, and we'll do that with the mean and the proportion. So what I have in front of us here is data from a class, and you can see that there are certain assignments that were done and how many points those assignments had possible, as well as these out here are extra credit, and students were not required to do those, but they could. And the direction that we're going here is I want to do hypothesis testing for the students who have completed all of the assignments. So the very first thing we'll do is remove any rows, any record of a student who didn't attempt an assignment, so where the assignment is a 0. And I'm going to do that by using conditional formatting to format a 0 with as red so I can easily see it. Now notice that I haven't deleted those rows where the student didn't do the extra credit. I'm only interested in rows where the student completed all of the assignments, the required assignments, and whether they did the extra credit or not is not important for this analysis. Now, we only need the last column here labeled final grade, and it's not actually the final grade because this course well, it's just not the last information. Oops, I'm just going to delete all of those, and we'll delete this row here. And so it's just the grade, so we'll call it the grade. All right, so now we have the grade for the students who have completed all of their required assignments up to this point in the class, and we can begin to work with hypothesis testing. And we're going to start with hypothesis testing for the mean. Now, one of the first things we want to do is run our descriptive statistics using the analysis tool pack. So we'll go up here and do that. Okay, we can see from this that the mean is 79 points out of 100, or 79% if you will, but 79 points out of 100 here. And the median is 79.65, so very close, which is a good sign when you're looking at these types of things for grades. Also notice that our kurtosis and skewness are both quite small, so these lend themselves to thinking about whether this is a normal distributed data or not. Our count is 34. And we know from the central limit theorem that if n, the count, is greater than or equal to 30, that we can treat this as normally distributed data, which we will. What is hypothesis testing? We're working with a sample, and we want to know what we can rightly say about the population from which this sample comes. And so we have competing hypotheses. One of them is called the null hypothesis, and the other is called the alternative hypothesis. The null hypothesis comes from the extreme critic, and this extreme critic essentially claims that you're not going to prove anything with your results. The null hypothesis is designated with H sub 0. The alternative hypothesis is a competing theory about your population. And so the alternative hypothesis states things in opposition to the null hypothesis, and it's designated by H sub A. Now, since we're making hypotheses about the mean, and we're making hypotheses about the population mean, we'll use the Greek letter mu. With the null hypothesis, we're making a claim about the population mean. And we'll use either the symbols, we'll use one of three symbols: the equal symbol, the less than or equal to symbol, and the greater than or equal to symbol. So we need a drop-down list. Now notice that I am putting a single quotation mark before the equal sign. Again, as I pointed out previously, Excel interprets an equal sign as there's a function coming after it. And so even in a list like this, it will create an error if we just put equal sign. So we need that single quotation mark before it to tell Excel that this is the text version of the equal sign, that it's not part of a mathematical formula. Okay, and now we have our drop-down list. And notice that when I select equals, that it doesn't display that single quotation mark. And then we'll be putting in a value here. So I'm going to start with 83. Now we need an alternative hypothesis, and the alternative hypothesis can be calculated from our null hypothesis. So we'll be changing these values. So let's put them in yellow. We can use a switch statement here to determine the proper symbol for our alternative hypothesis. So if the null hypothesis is an equal, we're going to use Excel's symbol for not equals, which is a less than as well as a greater than symbol. And if E18 is less than or equal to, we want the greater than symbol. And if E18 is greater than or equal to, we want the less than symbol. So we can test this out. It changes correctly to display our alternative hypothesis. Now this will simply repeat what we've put in for our null hypothesis. We can see from this that our null hypothesis currently reads that the population mean will be greater than or equal to 83, and that our alternative hypothesis is that the population mean will be less than 83. And if we change this to less than or equal to, then our null hypothesis states that the population mean will be less than or equal to 83. And our alternative hypothesis states that the population mean will be greater than 83. Notice how these hypotheses are exclusive. They're competing theories about the population mean. Now we need to calculate our T-statistic. And I'll copy in that formula so we can take a look at it. And okay, so what our T-statistic formula tells us is that T for certain degrees of freedom. Now those degrees of freedom are the count minus 1 for that degrees of freedom. So in our case it would be 34 minus 1, so 33. That the T-statistic equals X bar, which is the mean of our sample, minus the mu sub 0, and that is our null hypothesis value. So the way we have it set up right now, that would be 83. And we're going to divide it by the standard deviation, which we have over here in our descriptive statistics, 10.81 and change. And divide that, the standard deviation divided by the square root of the count, which again is 34. So let's plug that formula in. So we get a T-statistic of negative 2.09605. Now, that doesn't mean a whole lot. Ultimately, we're trying to get to the p-value. That's what we're interested in, and we'll talk about that as we get closer. To get the p-value, we need to also have those degrees of freedom. We'll be using those. And so we'll just enter that formula. Of course, that's the degrees of freedom for this T-statistic. Now we want to get the p-value. Now, there's going to be a different p-value depending on the null hypothesis. And we will either do what's called a two-tailed, a left-tailed, or a right-tailed p-value. Let's talk about what this means: two-tailed, right-tailed, left-tailed. With any given hypotheses, we're talking about the population, and that population has a certain mean as represented by this yellowish line here on this bell-shaped curve. Now, if we're talking about a two-tailed test, then the alternative hypothesis will use the not equal symbol, which of course for Excel is the less than as well as the greater than symbol. The two-tailed test also has the null hypothesis using the equal symbol. So we're saying in a two-tailed test that mu, the population mean, will equal a certain value. That's our null hypothesis. And our alternative hypothesis is that it will equal any value other than that null value, that null hypothesis value, the y. And that's represented by these shaded green areas. So what we're saying in a two-tailed test is that the alternative hypothesis can be accepted with a mean anywhere on the left tail or the right tail. Now, if we're using a one-tailed test, what we're saying is that the null hypothesis claims that the mean is greater than or equal to some value. This is shown with the shaded yellow area here. And an alternative hypothesis for a left-tailed test is that the mean of the population is less than or equal to that value, shown by the green shaded area here. And of course, it's reversed for a right-tailed test. In a right-tailed test, we're saying for the null hypothesis that the population mean is less than or equal to y, the yellow shaded area here. And for our alternative hypothesis, we're saying the population mean is greater than y for the represented by this green shaded area here. As you can see from this, we call it a left-tailed test based on the alternative hypothesis and the direction that that hypothesis is pointing. And we call it a right-tailed test based on the direction of the alternative hypothesis and the way that hypothesis is pointing. And let's be clear. What we're trying to do with hypothesis testing is to make some legitimate statement about the population based on the sample that we have. So even though we're picking a value for the null hypothesis to represent the population mean, we don't actually know the population mean. We're trying to determine, based on the alternative hypothesis, what we can say about the population mean. Thus, we need to calculate the p-value for the kind of test that we're doing. Let's enter the formula for calculating the p-value for the two-tailed test. Now, it uses the t.dist.2t for two-tailed, and the x value is your t-statistic, and the degrees of freedom are your degrees of freedom. Now, before I hit enter here, I want you to know that it's going to create an error, and I'll explain why. So here we get a num problem, a number problem. And the reason is that the two-tailed test, the function that Excel has, expects a positive value for the t-statistic. So we can correct that one of two ways. we can either use absolute value of D21, or we could use an if statement. If D21 less than 0, then the negative of D21, otherwise D21. So the absolute value is the easiest, so we can just retype this in. I could have changed the formula, but I'm just retyping it. There's the absolute value of D21. And then D22. And we have our two-tailed, our p-value for the two-tailed test. Based on our hypotheses, the way they are currently written, we've actually have it set up for a right-tailed test. So somehow we have to connect the output down here, two-tailed, left tail, right tail, to the symbols that we have here. So the best way to do that is with conditional formatting. Now I've selected equal to, and I'm going to put a 1 here, not because I care about what the value is here, and I'll explain later why not. We're actually going to be using a formula, but because I want access to these defaults. I like the green on green, I like the red on red, and so I can build that in, and then I can go back up here and edit it to insert the formula that I want. Now I could have started with the formula, but in that case, the default green on green would not be available to me. So I just prefer to do it this way. So what I'm saying here is if E18 equals the equals symbol, then I want it to be green on green. And let's test that. Well, this is interesting. Conditional formatting obeys the rules of relative and absolute references. So when we selected this and it pointed at E18 for this cell right here, which is what, D24, yes, E18 equals the equal symbol, but when it copies it down, it's a relative reference, so it's now looking at E19. So I'm going to have to edit that formula to include the absolute reference symbol so that both cells will work with what we have here. So you have to pay attention to the absolute and relative references for those. Okay, let's continue on and enter our p-value formula for the left-tailed test and the right-tailed test. And the left-tailed is simply t.dist for t-dot distribution. And again, it needs that x value, which is our T-statistic. And it needs the degrees of freedom. And for the left-tailed test, and only for the left-tailed test, we need to know if it's cumulative or not. And we want it to be cumulative. So here's the p-value for a left-tailed test. And we'll use conditional formatting to highlight these cells if we're going to do a left-tailed test. If we change it to this one, then we see that we have a left-tailed test. And we can do the same thing for the right-tailed test. And the right-tailed test is the t.dist RT for right-tailed. And all we need is the T-statistic and the degrees of freedom. And as you can see, all of these values are different, even though it's using the same T-statistic. And this is why we have to use the appropriate two-tailed, left-tailed, or right-tailed test to find our p-value. So there you have it. We can select the type of hypotheses we want, and we'll be directed to the appropriate p-value for that. Now, we can build that all into one formula, which is a great idea to do at this point. And of course, we're going to need to embed all of those formulas in to get that p-value. And it will have to be based on this symbol here in E18. And we'll also want to label that, whether it's two-tailed or left-tailed or right-tailed. So let me enter those formulas. So now we can get our labeling. That's correct. Now we simply have to take all of these formulas and embed them into one formula that solves the p-value. Okay, let's review this. So I have an if statement, and I'm checking to see if it's a two-tailed test by checking to see if there's an equal sign in E18. If there is, I'm doing the calculation for a two-tailed test, remembering to include that absolute value for the T-statistic. Then if it's not the equal sign in E18, then I have another if statement embedded in that one that will test to see if it's a greater than or equal to sign. And if it is, it'll do the calculation for the left-tailed test, ensuring that I have 1 as cumulative, because I want that to be cumulative value. And then if it's not either the equal or the greater than or equal to, then it must be the less than or equal to, and I don't have to test for that. I can simply plug in my last test, which is the right-hand test, and do the function for that. So now these values should match when I change my symbol up here. And indeed they do. Okay, so we'll highlight these to mark these as our final answer. Well, the answer for what? To find that out, we need several things. One of those is we need an alpha. So the alpha is the allowed probability of accepting a type 1 error. Of course, type 1 error is rejecting the null hypothesis when you should not reject the null hypothesis. And we get to pick that value. So we can put this in yellow because this is a value that we will adjust. And typical values are 0.1, 0.05, and 0.01. And those, of course, corresponded the significance levels of 90%, 95%, and 99%. So I've chosen a 95% significance level, which means a 0.05 alpha. And the way the alpha works in this is a p-value less than alpha means that I can reject my null hypothesis, recognizing that I've got some probability of a type 1 error, in this case a 5% probability or possibility of a type 1 error. Let's use our worksheet and these calculations to propose a hypothesis and test it. So let's say in this example that the university says that any course mean above 83 indicates a class that's too easy for the students. So we could say our null hypothesis is that the population mean, again based on our sample, would be greater than or equal to 83. And we're doing a left-tailed test, so our alternative hypothesis is that the population mean based on the sample that we have here is less than 83. So since we have this set up, we can immediately go down to our answer here, and we can compare it to that alpha. So the alpha is 0.05, and we see that the p-value for the left-tailed test is 0.02. It's smaller than the alpha, so we can reject the null hypothesis. Okay, let's set up a right-tailed hypothesis. Let's say that the university says that any class that has a mean below 73 is too difficult for students. So our null hypothesis is that the mean of the population is less than or equal to 73. That gives us an alternative hypothesis that the mean of the population from this sample, based on this sample, is greater than 73. And again, we can look at the results for the right-tailed test and down here and see that indeed the p-value is less than 0.05. So we can reject the null hypothesis. Now, what if the university said that the mean for a class should be 80? So let's do a two-tailed test on this. And our null hypothesis is that the mean of the population equals 80. Our alternative is that the mean of the population does not equal 80. And we can come down here and we can look at our results for the two-tailed here and here. Compare that against our alpha of 0.05, and we can see that the p-value is actually greater than 0.05, and so we cannot, or we fail to, that's the proper language, we fail to reject the null hypothesis. The mean of the population from which this sample comes might be 80, might actually equal 80. Thus, we fail to reject the null hypothesis because the p-value for the two-tailed test is greater than the alpha. Let's tackle hypothesis testing for proportion. Now you can see in front of you that I've copied most of the content from the hypothesis testing for the mean worksheet over to get this started for proportion. There's no need in us duplicating the work that applies to both of them. So I have the grade here in column A. I've got the descriptive statistics here for the grade. I've labeled it as hypothesis testing for proportion. We have our null hypothesis and our alternative hypothesis that work with that drop-down list, as well as our two-tailed, left-tailed, right-tailed tests that also highlight with that drop-down in E18. In addition, we have the combined test here for the p-value as well as our alpha. Now what changes is we'll have to calculate a Z-statistic. But before we get to that, we also need to look at the central limit theorem. So the central limit theorem for the mean is quite easy. N is greater than or equal to 30. However, it's not as straightforward for the proportion. Here's the formula that we'll be using. So it'll require an if, it'll also require an and function. Now notice that it uses the count in, it also uses the proportion, this p, which is the proportion from our sample, and we need to figure that out. So to figure that out, what we're going to do is enter a target score. So this will be a certain percentage. And so let's say 90%. And we will be changing this. Now what we want to know is the count of all those grades that are greater than or equal to, in this case, 90%. So we'll use a count if, and the range will be all of our grades. And the criteria will be this greater than or equal to, greater than or equal to. And we have to use the and symbol to join that, concatenate it with that G6 value. Now G6 is a percentage and we need whole numbers, so we're going to multiply it by 100. So that should get us the right count. So there are 70 who have a 90 or better, and we could change this to 80 or better, and it tells us how many have that. We'll just leave it at 90. And now we need to calculate that proportion for the sample. And that will simply be our count divided by our total count, which is, D16. There we go. So 21% or 0.21. Now that we have the p, 0.21 in this case, we can calculate our central limit theorem. I'm going to use an if statement with an embedded and. The first logical condition for that and will be our count, so D16 times G8, which is our proportion, and all of that, if that is greater than or equal to 5, it will be true, as well as the count times 1 minus that proportion, and if all of that is greater than or equal to 5, it will also be true, and if both of those are true, then I want it to display yes, otherwise I want it to display no. So it does meet the central limit theorem, and I could use conditional formatting to color code those, but I'm not going to take the time to do that. But we can see if it works. We can come down here to the count and just change it to 10 and see that, well, if it was just a sample of 10, we wouldn't meet that criteria. But we do meet that criteria, so we can move forward. When you copied your mean worksheet over to your proportion worksheet and began to make the modifications, you would see this number error here. And that's because as we copied it over, we have the T.dist function in there, and it's pointing at both D21 and D22. Of course, neither of them have any values in them at this time, and we're not going to put a value in D22. We don't need the degrees of freedom to calculate our two-tailed, left tail, and right tail for proportion. And we're also going to use a different function. In fact, we're going to use that norm.s.dist function. And it's easiest to start with our left-tailed, and you'll see why in a moment. But we're going to use that norm.s.distribution. And for our z, we're going to include the z value that we have here. Now, we haven't entered that yet, but we'll get to that part. And then it's going to be cumulative. So we'll have some value in there. Now, it's essentially interpreting that z as 0, so it gives us a value. Now, the reason the left-tailed is easier to start with is because when we come over to the right-tailed and you think about what is left-tailed and what is right-tailed, we're simply subtracting that left-tailed from 1 equals 1 minus our norm.s.distribution. And of course that'll be the same z and same cumulative. And that will give us our right-tailed. Now notice at this point they're exactly the same because we're dealing with a Z-statistic of 0. Now for the two-tailed, it is simply 2 times the right-tailed. And much like the two-tailed for the mean, when we're doing the two-tailed for the proportion, we also need to use an absolute value, and otherwise we'll get an error. So we have 2 times 1 minus that norm dot s, and now we want the absolute value of our Z-statistic in case it is negative, and that will give us, oops, I forgot, a closing parentheses. So again, Excel is kind in prompting me for that, so that's a good thing. So now we have the correct formulas in there for the individuals, and we need to build the combined formula. And so we'll just include, we could modify the one that's there, but it may be easiest just to start over and type the whole thing in. That's your call, of course, when you're doing this on your own. Okay, and now those formulas should work. And the next thing that we need to calculate is that Z-statistic down here. So the Z-statistic uses this formula. And the Z-statistic equals that proportion percent, or the proportion for the sample, the p-bar, which is that 0.21, minus the proportion for our null hypothesis, which currently is set at 0.8. We really haven't messed around with that. Then all of that is divided by the square root of the proportion for the null hypothesis times 1 minus the proportion for the null hypothesis, all of that divided by n. So let's implement that formula. Now note that because I copied this over from the mean worksheet, that all of these calculations are already pointing at D21. And so once I do this, then my two-tailed left tail and right tail, as well as my combined formula, will work correctly. So this equals G8 minus F18 is where that null hypothesis value is, divided by the square root of, we have F18 times 1, whoops, times 1 minus F18, and all of that divided by our count, which was D16. So now we have a Z-statistic, and now we can begin looking at a scenario, creating a hypothesis about a certain situation. Let's consider a scenario where perhaps the university says that no more than 35% of a class should get A's. Perhaps if more than 35% of a class get A's, the class is too easy. So we can set our null hypothesis to 35%. And this is going to be a left-tailed test, because the null hypothesis would be that the population proportion that is identified by this sample is greater than or equal to 35% have an A. So our alternative hypothesis is that that proportion for that population based on this sample is less than 35%. And we can come right down here and look at our left-tailed and compare it to our alpha, and we can see it's less than the left-tailed test p-value is less than our alpha. We can reject the null hypothesis that the population proportion for those who will receive an A is greater than or equal to 35%. Let's consider a situation where we can look at a right-tailed test. So let's think about maybe the university says that at least 80% of students should pass a class, otherwise perhaps the class is too hard. So we can put in the passing grade of 70% here. The university is saying 80%, so we'll enter 0.8. And our null hypothesis would be less than or equal to. The null hypothesis would claim that the proportion of the population that will pass this class is less than or equal to 0.8. So our alternative hypothesis is that more than 80% of the population proportion would pass this class, again based on this sample. So we can go down to our right-tailed test and our alpha, and we see that the p-value for our right-tailed test is greater than our alpha, so we fail to reject the null hypothesis. Okay, so we've demonstrated how to do hypothesis testing for the mean and hypothesis testing for the proportion. Now it's your turn to try.